Well, again, welcome everyone to our University of Minnesota Extension Agrivoltaics webinar series. Excuse me. My name is Sabrina Florentino, and I am the Alternative Livestock Systems Extension Educator. Perfect. So as I was saying, Sabrina Florentino, I work with Extension here, and I also worked with Dr. Brad Hines, studying agrivoltaics for my master's degree. So today we are going to be talking about growing forages as well as grain crops. So we have a group of farmers with us as well who has been taking on the very interesting project of putting solar panels in their row crop fields. So we'll talk a little bit about forages and grain crops. So if you have been joining us throughout the series, we've already had a webinar discussing cattle solar grazing research, so grazing cattle under solar panels. And then we also had one about sheep grazing under solar panels. So now we're moving into our forages and grain crops, and we will be having another webinar in August, which I'll remind you about at the end. But as I mentioned, or as in the past, we have recorded these webinars, and this one is also being recorded. So it will be shared with you when we are finished, and we will send that out to all who have registered. So as I mentioned, tonight, myself and another team of farmers will be presenting. I'm Sabrina Florentino. I joined Extension about 1.5 years ago and have worked, as I mentioned, with agrivoltaics during my master's degree. I work with alternative livestock systems. So agrivoltaics, again, falls into that as we are grazing cattle under solar panels. But in general, I'm usually working with pasture-based producers, organic, mobilely housed livestock, those types of things. At this time, I would have John Baumgartner, Raleigh, and I don't think Larry's there, but introduce themselves and a little bit about how they got involved with agrivoltaics.
Okay, my name's Rauenhorst. My brother Larry came up with this concept of putting solar panels above the crop and farming row crop underneath it, probably 3.5 years ago. Anyway, I'm basically a retired mechanical engineer, worked in agriculture and pretty diverse product lines. Actually did consulting engineering, so from industry through agricultural equipment, large stuff and small stuff. So pretty wide, varied career, over 25 years. And I farm part-time, or I have farm acreage that I rent out as well. So stayed involved in farming throughout the years.
I'm John Baumgartner, first cousin to Raleigh and to Larry. And I'm retired as well. During my career, I did a number of things. I had a company for 40 years where we developed a number of products to help farmers overcome things like odor and the like that were coming off of lagoons that were being built for larger livestock facilities. And that evolved into a ionization technology to help purify the air and control disease inside large livestock production facilities as well. Before all of that, I spent some time in government, and a long time ago now, but I was, for a while, for about 3 years, I was the Assistant Commissioner of Agriculture for the state of Minnesota. And for about 2.5 years, I was appointed in the George Herbert Walker Bush administration to be the Midwest Area Director of ASCS, Agricultural Stabilization Conservation Service. and that involved 8 states in the Midwest. In retirement, I've taken to both Larry and Raleigh, helping them in the shop to do various things. And this project really caught my eye because somehow, sometime, somewhere, we have to stop using fossil fuel. And this project that we're working on is the closest I've ever seen to a technology that could meet that demand. And if we were able to do that, we could slow down and basically over some time stop climate change. It's just the idea here is so important. I can't express enough excitement about it. And we do really appreciate the University of Minnesota participating with us to document the yield differences that we might see with an elevated solar array versus not. And I believe the solar array itself is elevated about just about 14 feet above the ground. And the different arrays are separated by what, north and south, how many feet is it? 60 feet. 60 feet, east and west, they're 40 feet apart to allow tillage, planting, and different things underneath. The solar array is also designed to tilt to the south during the summer as the sun's position changes, and every day rotate from east to west, following the sun to maximize the surface contact with sun ray.
Look at it. This is just
introduction.
All right.
No, very good detail, and like, don't mean to interrupt, but we can, discuss those really awesome details with the slides, and the pictures as well will be very helpful for the audience to see as you're describing. So, but thank you for those wonderful introductions and really detailing the experience and wealth of knowledge that you guys bring to this team. And hopefully as we share more about the project, it'll become clear how great it is to have the three of you working together to make this come to fruition. So thank you for your introduction. We will move into a little bit about our forage research here at the University of Minnesota. Agrivoltaics, again, the reason we're having this webinar series is due to Dr. Brad Hines and the work that he's been doing at the West Central Research and Outreach Center, both mostly in the context of organic dairy farms. So as I mentioned, we had our cattle solar grazing research webinar earlier, and we discussed grazing cattle under the solar panels. And of course, we're producing energy at the same time. And in this instance, we're going to talk a little bit about growing forages. So in Brad's presentation in our very first webinar, he did mention this study. And so I'm just going to go into it in a little bit more detail and what we found, and then tee it up for the Rauenhorst team to share about the row crops. So just taking a step back, agrivoltaics is agriculture and solar energy production on the same piece of land. And this is of interest because we're losing available arable land in order to continue to feed the world and all the other products that come from agriculture. So the literature and the different ways that agrivoltaics has been employed so far, whether that's livestock or vegetable crops or row crops or forages, the estimates have shown that putting agriculture with solar energy increases land productivity from 35 to 73%. And that, in a similar vein, the land equivalent ratio is going to be greater than 1.5. So what does that mean? That means when we have, we could have crops being produced on 100 acres on one side and solar energy being produced on 100 acres right next to it. But when we combine the two together on the same piece of land, we actually see some synergies exist that increase the production of the two together. So we could produce the same amount or of product of crops and energy as 150 acres of land when we compare to those two things being on separate pieces of land as opposed to together. So when we put the two together, we see increases in productivity, and with that, an increase in income for farmers, anywhere from 2.5 to 35%, depending again on what we're growing in our systems. And frankly, the way that the solar panels are set up and the way that the solar site is designed. So that's just what has been found in the literature so far, but there's always need for more research, and especially climate is going to, different climatic conditions are going to affect these things, and amounts of rainfall and things like that. So there's always need for more research in our particular context and with the particular crops that we are growing in a specific area to really know what the impact would be of combining these systems together. So for our study, it occurred at the University of Minnesota West Central Research and Outreach Center in Morris, Minnesota. Here are just a few pictures of the West Central Research and Outreach Center. And you can see there in the top right, the 50 kW solar site installation, which is one of the sites that we did grow forages underneath. And then just some pictures of the dairy cattle that are on this farm. There's also swine on the farm, and there's panels on the swine barns. But for this study, we worked with this 50 kW and one other site. And what we were really interested in is just what can we grow underneath the solar panels? We know we can graze underneath. Are there other opportunities for forage production? And we even threw some grain crops in there to see what would happen, which proved to be a bit of a struggle. But so this is mainly focusing on the forage crops, the grasses and legumes that were planted underneath the solar panels, both the biomass that was produced as well as what sort of nutritive value did those crops have. So we wanted to evaluate the agrivoltaic site effects. So the each site was a little bit different. So we're really looking at the different solar sites and how they affected the crop growth. And as I mentioned, this occurred on the organic dairy farm. So we grew these forages in an organic context and with the thought that you would then feed them to dairy cattle. So as I mentioned, we had the 50 kW that we were looking at, which is basically creates a complete cover of shade, and there weren't cattle grazing under it. And this is near some calf hutches on the dairy farm. And it would be a flat top design with reflectors. And then we also had on the bottom left a 30 kW ground mount, which is two 15 kW arrays. And those are in a cow pasture behind the office building on the West Central Research and Outreach Center. And then we planted a number of forages. Here you can see we had alfalfa, field peas, meadow fescue, orchard grass, red clover, sorghum Sudan. So we had some warm season grasses in there. One warm season grass, white clover, and then a few grass and legume mixes, both or with alfalfa, red clover, and white clover as well. So we had replicates of each of these in each of the solar sites. And then we also had a control site, which was established in an open air pasture to compare to. So again, pictures of the 50 kW, one of the sites we were planting underneath, and the 30 kW. So this would be before the plots are established, and they're in perennial pasture in these pictures with the cattle underneath. And here's just showing a good observation of the shade that is occurring in the 30 kW. So in the 50 kW, everything was covered with shade, and then the 30 kW, we have partial shade, full sun, partial sun. So that's why we're really comparing like the two sites to each other, and they were pretty different. So what I'm showing you here, these results are very specific to these solar arrays, and you might have different results in different designs and different setups, which we will see with the row crop project that's coming up. So to prepare the sites, you can see on the left again our control in the open air pasture. We had 2 tillage passes, and then again, it's an organically managed land, and then we established our plots with a plot seeder about mid-May, and this was during 2022, the growing seasons of 2022 and 2023. So in the middle, you can see the 30 kW arrays, and then the second picture from the right is the 50 kW, and the control again on the very far right. So we did have some plots in our larger solar array as well. And I just throw this in there to share some of the story of this research, that you can see this aerial picture of the plots there, but what you're seeing is really mostly weeds. And I guess that's a product of the weather for that year. You know, we had a really wet spring in 2022, and then into the summer, it was a drought. So, you know, all that really survived down there in this more sandy, gravelly soil was the weeds. And so we weren't able to continue with those, but that was the intent. And I just bring that up because if we're thinking about establishing a forage stand or some other crop under the solar panels, you know, if it started in a perennial pasture, we have to think about how we will transition from grass to something else, and you know, have the same thought process. Depending on how the panels are constructed, it might be more of a construction zone that you're dealing with after they have been implemented, and then you have to think how to best establish a crop after that. And well, again, we're in an organic system, so we didn't have herbicides to help with this issue. And so just keeping that in mind, if you are thinking of implementing some sort of agrivoltaic system, is how much disturbance will there be to the soil when the panels are put in, and or, you know, with your own establishment of the forages. So with that, I wanted to just walk through a little bit of what we were seeing throughout the season in these plots. Here we have the full sun control, and I show 2 different species. There's grass alfalfa mix on the left and sorghum Sudan grass on the right. And we had a pretty good emergence. Again, I mentioned we had some good rains in the spring. But later on, you know, things sort of dried up, and we did have more weed pressure in the control area as well. In the 30 kW, we had some plots that would end up in the full sun most of the time, just due to the spacing of the panels. And then we had other plots that were in partial shade, partial sun. And so here I'm showing the same species. We have grass red clover mixture, and in the full sun, we can see the emergence is coming pretty strong. In the shade, it's a bit patchy, but as I mentioned, later on in the season, we were in drought conditions. And so actually the grass clover mix in the shade later in the season did much better because of the shade, you know, helping to retain more moisture in the soil. So we saw some differences throughout the season, just depending on how much shade each plot was getting, and of course with the weather conditions. Here's a picture of the 50 kW, which had full shade, so there was less variability, and therefore our emergence was pretty uniform and uniform across species. So there's some red clover here and then orchard grass, and that pretty much continued throughout the growing season. So to collect our data, we, as I mentioned, this occurred in 2 seasons, 2022 and 2023. We clipped biomass samples once the forage, the majority of the forage reached about 12 inches, and then we mowed those plots after we took our samples and allowed the perennials to regrow, and then harvested those 2 or 3 more times throughout the year, depending on the year. And then those samples were dried, and we did botanical composition of the samples, and then sent them off for nutritive analysis as well. Here's just a picture of the weather for those 2 growing seasons. We can see that 2023 was slightly warmer than 2022 across the board, but 2023 did have more rainfall. 10-year average rainfall for Morris, Minnesota is about 21 inches of rain, so both years were definitely dry compared to normal. And here we're getting into some of the results of the forage that we grew under these panels. So we saw that, as you would expect, our second and third cuttings, we had lower biomass, and then in 2023, we actually had lower biomass for each cutting compared to 2022. And that would just be all of the forage species averaged out. And then when we look at our different species by solar site or control site, we can see that. So just to, I guess, orient you a little bit, we have in maroon, we have the 30 kW. So that would be the agrivoltaic site with partial sun. And then in yellow, we have the 50 kW, which was the pretty much complete shade solar site. And then the gray is the control site out in the pasture. And then I have here some solid red circles, which are indicating a significant difference between the sites. And then if it's a dotted line, it just means that they were similar. So, you know, at first glance, we see biomass that the control site probably produced on average more biomass, but really that comes down to 2 different species, the field peas and the sorghum Sudans, which are both, you know, warm season sun-loving plants species. And so it makes sense that they would have had produced more biomass out in the sun and not under the panels. But when we take a look at our cool season forage species, we see that pretty much across the board, the 30 kW at least was similar to our control site in forage biomass produced for, again, pretty much all of the cool season species. With our 50 kW, again, it was full shade, so there was a couple that they were similar, but that site definitely produced less biomass for the forage species that we had out there. So then we're also interested in the nutritive value of those forages and what sort of value they can bring to, for in this example, the organic dairy. And first looking at the 50 kW, we see that it's pretty high in protein for most of the species. And we think that's mostly a factor of maybe the maturity of the plant and the less biomass that was produced, you're going to see a higher protein content usually. So for the 50 kW, it was pretty high in protein for a number of the species. And then if we compare the 30 kW to the control, we see that there was either similar or higher crude protein content compared to the control forages. Then looking at neutral detergent fiber, so this is a measure of the fiber in the feed, and again, pretty similar across the board for the forages and NDF content, with comparing the agrivoltaic sites to the control sites. Except for the grass alfalfa and grass red clover mix, there was slightly higher NDF values for the agrivoltaic sites. But when we looked at digestibility of that NDF, we do see that the solar site for those two mixes was higher. And again, across the board, pretty much either similar or higher total tract NDF digestibility for all of the forages compared to in the agrivoltaic sites compared to the control sites. And then we have relative forage quality here, which again is another measure basically of digestibility and availability of those nutrients. And, you know, if we're looking at dairy quality, hey, we're looking for RFQ of about 150. So we can again see that the forages produced in these agrivoltaic sites are of high quality and high digestibility compared to the control, and either similar or higher amounts. So with that short spiel of the data, we want to conclude that we can produce comparable biomass in at least the 30 kW, so a solar site that has a little bit more sun in between panels, in between arrays, and when comparing that to an open control site. Again, we saw less biomass was produced in the 50 kW, which you see a picture of that here, pretty much completely shaded. But the forages at the agrivoltaic sites were similar or higher in crude protein, fiber content, and digestibility as in overall forage quality. So with that, we think agrivoltaic forage production can provide high quality feed for a dairy farm in this case, energy, and hopefully additional income for farmers. And so, I mean, another take-home message, you know, to think about is we were establishing these plots with research equipment, and so there's lots to be thought about of the logistics of either producing hay under panels like this. And as I mentioned, we did have some grain crops that we planted, and just anecdotally, we had, you know, wheat and oats that really were thriving under those panels, but we just weren't able to harvest them, unfortunately, due to some deer pressure. But there are definitely opportunities to produce a wide variety of crops under these panels. But again, just thinking about the logistics of how that will happen and what equipment can and cannot be used. And I think with that, we will learn even more about that topic from the Rauenhorst team, who has thought a lot about that and how they can grow corn and soybeans under panels as well. So with that, we will transition into the Rauenhorst team and their project growing row crops under solar panels. And again, if you have questions, please put them in the chat and we will get to them at the end. So we will transition to the Rauenhorst team now.
My brother Larry is here now. I don't know if you can see him on the camera. There he is. He's the one that basically came up with this concept of farming under solar panels that are spaced out fairly wide. We're only covering about shading about 7.5% of the ground or surface area. And so we ran some back of the napkin kind of numbers on this. And in 2019, there was 166 million acres of just corn and soybean row crop being farmed in the US. And our current electricity production in 2019 was about 4,000 terawatt hours per year. To produce that much electricity on that 166 6 million acres of cropland, you would only have to deploy this kind of system on about 15% of the cropland. The total energy use in the US ends up being, in 2019, was about 97.3 quadrillion BTUs, which converted to terawatt hours is about 30,000 terawatt hours. But when you burn fossil fuels, you only get about 30 to 40% of that energy to do actual work. So to match that with 80 to 90% efficiency electricity for travel, home heating, and air conditioning, basically all the power that we consume in the US, manufacturing, etc., that could be replaced by 16,000 terawatt hours of electricity produced. And that would take just under 60% of that 166 million acres deployed with a system like this, covering 7.5% shade to the crop. However, since 2019 and since we put these panels up, the efficiency just keeps going up on the panels. Some say that within 2 years, we'll almost double what these panels have, up to over 40% solar efficiency. So that would automatically cut that acreage requirement in half. Anyway, so what we came up with after many iterations was a 36 kW total system output. There's 80 540 watt panels. We have 20 1800 watt microinverters, 2 microinverters for each tower that's out there. There's 10 towers on about 0.65 acres. And like I said, 7.5% shade to the crop, with shadows being widely dispersed due not only to the height of the panels and the staggered rows, but also dual axis tracking, which throws the shadow more effectively than if they were stationary. So here's the current basic layout. There's 4 rows of panels, 3 and 2, 3 and 2, and they're 60 feet north to south and 40 feet east to west. So a 16-row, 30-inch row spacing planter fits right in between the panels. Kind of an evolving concept. We had 10 panel systems, 20 panel systems, all kind of laid out, looking at the different shadowing and the percentage of crop coverage and so forth. Probably did 23 plus iterations of the design. When it came to putting them in the field, we developed a 3,000-pound hammer to drive the poles directly into the ground, and we used oil field piping as the tower support, 8-inch Schedule 80 pipes. And here we started to build stuff. These are braces that hold the roots to the towers so that they won't twist when the wind gets a hold of the solar panels. Just fabricating in the shop, putting and there's the finished towers. And here's the 3,000-pound hammer. And our first test run trying to lift it up with the backhoe and seeing what was going to work to handle this thing and get it up in the air. And initially we just had a hook on it. We eventually went to a chain and found that just letting the chain go slack as you dropped it worked better than having a hook on this ring. And here we are. I believe that was in the winter of 2018, 2019. To avoid compaction, we're out there at about 10 degrees. Use a 2-foot bucket to chew through the frost, and then did a pilot hole about 5-inch diameter, 3 feet deep. Stood the poles up with the hammer on it, and then drove them into the ground. And there it is in the ground, and the only thing left is to drive in the 2-inch diameter Schedule 40 pipe, 12 feet long, to act as roots to keep it from rotating once the panels are installed.
Then oil pipe.
Yeah. And here's a quick flyover of the layout. So on the site, we also installed a climate controlled data solar shack is what we named it. Built out of an old refrigeration unit. And all the electrical connections are hung on the side of that. Eventually there'll be a small table or desk and chairs inside. Getting ready to load it on a trailer and haul it out to the site. Part of this is of the design was the tilt mechanism. It tilts north and south, east and west, rather than the conventional angle towards the sun and then rotate. I found that looking at the shadows and how they're dispersed over the field, this was the most effective way of not leaving any part of the crop under the shadow any longer than necessary. Or this is the most dispersed that shadow would be by tilting north, south, east, and west. And here are the panel mount assemblies with all the tilt mechanisms, the linear actuators installed. And there's the 1800 watt microinverter that connects 4 panels. And there's John out there doing touch-up paint. That was his passion project, if you will. He spent a lot of time painting parts. And we're test fitting the first 2 solar panels in the shop, make sure we could fasten them. And a little preliminary wiring layout with the inverters. And loading up in the spring, getting ready to haul them out for installation out to the site. And there they are staged on the site before planting. And there they are with all the mechanisms installed. And a quick flyover again. And installing the panels. Here's a little time lapse of installing panels. And of course, the crop is already growing, so we're doing a little damage to the crop, but trying to be as careful as possible.
They look like monkeys.
And there's the last panel going up. And the completed installation with all the panels tabled. And then this spring, the U of M outreach brought their electric tractor, and we had made a small field cultivator to work up and level the ground. And testing a 4-row planter that we put together. The wheels on the electric tractor didn't line up on 60-inch centers, so I had to design and build wheel extensions for the tractor. And there it is, actually working the plot. And there we are planting the plot. And there it is with the soybeans up, and you can see the water in the background. We've had massive rains this spring. Fortunately, none of this area where the test plots are underwater, so. And that's about it. We're still working with our local red trying to get connected under the net metering statute, and they are refusing so far at this point to allow us to connect and receive net metering, which would allow the retail rate reimbursement for any excess electricity. And currently we're only using the electricity out there to control that small solar shack, power the tilt mechanisms to track the sun, but we're not currently producing any electricity. Occasionally we go out and charge an electric vehicle. Larry has electric car and electric pickup, so eventually we'd like to have robots not only planting, weeding, and then eventually harvesting the crop grown under the panels. So that's basically it.
Thank you, Raleigh and Larry and John. Could you share a little bit more about what you've seen with the crops so far in the panel system?
Well, last year with the corn in there, you know, we had damaged a fair amount of that, dragging scaffolding through there as careful as we tried to be. There did not seem, I mean, this is only anecdotally looking at the corn growing under the panels. There didn't seem to be a lot of variation where the shadows fell on the corn versus the rest of it. We unfortunately didn't get any real harvest data or yield data off of that. So far this year, I don't see any variation in the soybean growth, any discernible variation. It's all pretty even.
Even though it's fixed.
So, well, some of it's fixed. They're out there actuating. We're having trouble with some of the actuators failing early, but we have 6 of them that have been running consistently since the crop was planted out of the 10. Have more controllers on order and more parts on order to get those fixed, but in any case, I've noticed at the end of the day when you go out there, it's about 20 minutes before sunset before you see any shadowing from one tower to the next. I mean, the sun is almost set at that point. And otherwise, the ones that are tracking the sun should be producing near maximum output for the duration of the day, you know, except for 20 minutes after sunrise till 20 minutes before sunset. So.
Sure.
Go ahead.
So are there plans to get that yield data and or other data to be collected?
Yeah, we hope at this fall to have a weigh wagon out there and a harvester, which we've yet to set up how we're going to harvest them yet, but we'll find something. And then harvest under the center of that array get, mark out a specific area, which will be about 0.4 acres that are fully influenced by the shading from the panels. And then we have a test plot on to the north and to the south that we can do full sun comparisons. So
Perfect. So yeah, we look forward to getting some updates as the fall rolls around
yep.
on the project. Yeah. Could you speak a little bit about, your sourcing of materials and the economics of building this sort of solar site, and any things you learned along the way?
Yeah, well, the process of finding the materials was made easier by my brother Larry finding a local solar uh, installer. His name's Aaron Bussey from Glencoe. He has Minnesota Renewable Energies. Other than that, we sourced as much used material for building as possible, and we found it kind of ironic that the cheapest thing that we could find was used oil piping out of the oil fields in North Dakota. The entire amount of steel that we put in there, it would have cost us about that much for one of the towers. So that worked out fairly well. Other than that, from the time we started, solar panels were putting out just over 400 watt hours per panel, and we ended up, by the time we actually purchased panels, they were over 500 watts per panel. So that drove the design, some of the design changes right to the end. Other than that, the biggest challenge has been trying to get the co-op to allow the net metering, and gone through the Federal Trade Commission, the Public Utilities Commission, the Attorney General's office, a lawyer to send them a letter, and I'm currently working with Senator Tina Smith's congressional aide, who has put me in touch with a solar advocate group, and they are in discussion with their lawyer to see what can be done, because the law is clear, but none of the no one wants to enforce that, is what it amounts to. So I've contacted our county commissioner, who's talking to board members of the co-op, and they feel that it's unfair to the other members because this was not an existing service before we started this project. Even though you can have a farm site, put solar on it before you build anything on that farm site, and they've done that in the past. They just refuse to do it in this case because they don't want other farmers to get the idea that they can put in a 40 kilowatt system in their fields and sign up for net metering. Even though we have this set up to charge electric tractors, to charge our trucks, and so forth. As we convert more to electric economy and harvesting equipment, trucks to haul the grain, even a dryer on site potentially, or a fertilizer anhydrous ammonia production plant, small enough to cover, a particular field. That's all going to draw energy. And the beauty of this system, when you look at it around the country on the breadbasket, of those 166 million acres, there's a vast network of utility lines going to all these farms. You drive by any farm that has a grain drying site on it, it has typically 3-phase power and huge power lines running to that. And it's distributed throughout the US, anywhere grain crops are grown. So it's kind of an opportunity for, the way I look at it, for a co-op to take on this and offer it to farmers, say, hey, we can install this system on your cropland, pay you $100 or $200 an acre per year to have it on there, and you still get to raise a crop. And if you can get 15% of the farmers to buy into that, you've now produced as much electricity as the US consumes in a year. So
It just makes sense.
and from what we see, the research I've done, the few places that have this has been tested on other crops, and I only found one that had done it on corn, they saw no yield reduction up to 10% shading. And that was with fixed panels, not with tracking panels. So that's basically what we've been looking at.
We do have a question in the chat wondering if you have data on what the energy capture would equate to for a year.
Roughly 300 kilowatt. I really don't know. It would be, if we just had, you know, a couple of days or a week of data coming off these panels, it'd be a lot easier to estimate, but I really don't know. Typically tracking, single axis tracking produces between 30 and 35% additional energy. Or no, it's more than that. It's about 75% more energy. When you do dual axis, it's almost double the energy of stationary panels.
Could you give a little detail about the considerations for where to install the panels, what you were looking for a particular site? Were there any agronomic considerations and where to put the panels?
Not really. I mean, we just wanted an even spot in the field that was close to, you know, close to the edge of the field, so we didn't have to run a ton of wire. Originally, we wanted to piggyback off of an existing transformer, but our co-op really dug their heels in and did not want us to do this.
There was a question, how deep are the wires trenched beneath the field?
We went with at least 24 inches.
And what was the decision making behind that?
That particular piece of ground has been strip tilled for about 8 years, and strip till only goes down, what, 8-10 inches. Don't really ever see it being tilled anywhere close to 2 feet, and that's all that's required is like 18 inches.
So similarly, have you seen any strong storms and or other things that might impact the panels? And what did you think about in the construction of the panels when it comes to weather? There's a question here that they have winds that blow as much as 125 miles per hour. How would you design a solar site to withstand those?
Right, and these right now are capable of, without bending or distorting the metal, if they're deployed straight into the wind, as flat as you could be, they'll handle about 45 miles an hour for wind. And then when they're tabled, they should be good up to 120, 125 miles an hour. And there are anemometers on each tower currently that monitor wind speed. And so when the wind speed gets above about 30 miles an hour, they'll table themselves.
Do you know how many days a year that you get sun throughout the year?
Even if you don't get sun, they do produce energy, but I guess I don't have that data sitting in front of me. I know when we calculated it, it was like just under 70% of the days in Minnesota have about 70% of daylight hours have diffused to strong or full sun. That includes days where the smoke is thick in the sky from Canadian fires and et cetera.
Sure. So again, participants, if you have more questions, just put them in the chat. There was a comment if we can see the everyone chat, and I believe we can. There's, I guess, one question that related back to the study that I discussed, wondering about forage digestibility, and those samples are sent to a lab in which the forage is basically put into rumen fluid from a cow to mimic the digestibility that, or the digestion that would happen in the rumen environment of a ruminant, and from that they can determine the digestibility of the forage. As a solar project, agrivoltaic project, what are your thoughts about, do you plan to put more panels on your land in the future? Again, you're having issues with connectivity, so that's probably a hindrance, but say that wasn't a hindrance, what would be the future of projects like this?
Well, as I see it, if you have a field strategically located near a power substation, this particular field does, and what is there, Larry, 320 acres contiguous there?
Yeah.
Yeah, I mean, the entire field could be done that way. However, not looking to do that on our own because the cost and the effort to install it is pretty great, as you can imagine. If you designed equipment that with a pneumatic or an impact hammer to drive those poles in, you could carry half a dozen on a high clearance row crop machine, go out in growing season, pound the poles in, or do it in the winter time, whatever. Installation could be made very quick. You could carry the pre-wired panel assemblies out there with a small winch on the same machine that pounds the panels in, winch them into place, throw in the bolts to on top of the tower, and carry between 2 and 4 assemblies at a time, or more, depends on how big you make the high clearance installation machine. And done on a large scale, I can see the equipment installing up to 10 acres a day. That'd be upwards of 125 or 130 poles, but it wouldn't take that long with the with the right equipment.
Sure. And so if we did have these panels across the fields, could you reiterate what sort of equipment you've been able to use underneath? So you meant, can you use full-size planter, harvester? And you showed some pictures there of the electric tractor. But was that just to show the use of the electric tractor, or could you also use larger machinery?
Tractor and how much energy it took to actually till the ground and to plant the ground. So Eric and Peter and have that data as to what that took. Now, most farmers today, as you know, have RTK GPS guided tractors, and they don't really have to touch anything. So properly set up 16-row planter could plant right underneath there, on a 30-inch spacing. My brother's current renter has 16-row planter. Well, it's actually 32-row because for soybeans, because it does twin rows. And because of the way that's set up, it's a lot wider than it would necessarily need to be. So he would have to wiggle around the poles a fair amount. Again, not a problem if you have guidance that can take into account curving around the poles. All it would mean is a little more gap than would absolutely be required if you design a planter for it. But ultimately, we'd like to see 4-row equipment. Instead of having, say, a 40-row planter, have 10 4-row planters that are autonomous. And now you don't have the problem of dragging them down the highway and making everybody run into the ditch when they see you coming. You could just put 4-row equipment on the back of a semi, put 10 of them on there, and drive them to the field, unload them. If one row goes bad, you only lose 4 rows of planting. The other 9 are still out doing their job. So there's some efficiency to be had if we get to smaller equipment that's autonomous. That technology is pretty much already out there. You can have it go back and exchange a battery at your, in this case, our little solar shack. Ultimately, I see that being a large battery bank there that helps level out the grid, so it will operate throughout the night. Also, when you're out using high amounts of energy, you can draw off of that to recharge your battery packs and run your equipment.
Just like here.
Yeah. Just in the last couple of weeks, been working with a robotic lawnmower that will cover up to 6.5 acres, and it's all run off RTK, and it goes out. Right now, it's out mowing all on its own. And when it's done, it comes back and automatically backs itself onto its inductive charge pad and charges itself back up, and it's ready to go again as soon as the battery's charged up.
Yeah, that's quite the vision of the future. So thanks for clarifying that. There's some clarifying questions in the chat. Did the co-op provide you with an interconnection agreement and that has moved forward, or are you still waiting to receive the interconnection?
They actually sent us a contract, and we chose the option for net metering, and then they refused to honor it. And they place at one point, they said, well, we'll offer you 6 cents a kilowatt, which is half. And now they're down to 3.1 cents is all they want to offer. And the retail rate is 12.2, I think now, or 12.3. So, I mean, when we looked at it, the project paid for itself in 6 to 7 years at retail rate. At 3 cents, it never pays for itself.
Yeah, well, thanks for taking the risk and putting panels out in the crop field and sharing your story with everyone. And we're looking forward to hearing more in the future, hopefully. And we just do have one more question to pivot back to, is wondering what sort of mower that was that you were talking about.
It's called Yarbo, short for Yard Bot. And it is about 230 pounds. It has tracks and a mowing module that sits out front.
Caterpillar.
Yeah, it looks like a little cat. It's yellow and black. It looks like a little caterpillar.
Perfect. But again, thank you for joining our agrivoltaics webinar series. There will be another one on August 19th, discussing a few different agrivoltaic projects from across the country, and spanning everything from livestock to, again, crops and vegetable production. So please join us and hear from a number of professionals in the field, both solar developers and livestock producers and nonprofit organizations working to advance agrivoltaics. So we hope to see you on August 19th at 7 p.m. I have the link there for you to register, and it will be sent out again to anyone who has registered for this one. So we thank you for joining and hope you have a wonderful evening.